So let me talk about the capstone project. So what I did is, given that it's only 2 weeks left, I changed the nature of the final project. So instead of being more open-ended, it's more like a capstone kind of a thing, just wrapping up what we have done in the course. So the capstone is to implement AlphaFold 2, right? So that's essentially a little bit simplified version of AlphaFold 2. So if the campus wire note that I sent out, the idea is that we'll implement this in the next 2 weeks. Okay, so you got 1 week per part. So there are two parts. The first part is the Evo former main trunk, which we've been talking about, and I'll talk about that today also. So that's basically taking the sequence information and then creating those abstract representations through the multi-layer Evo former convolution and things, right? So that's part one. Okay, now for part two then, right, we haven't yet actually generated the 3D structure completely. So that's what part two will do. It will actually then take the second part of AlphaFold, which is this IPA or independent pointwise attention module with some sort of structure computation on that. So I'll of course talk about that in my lectures, but then that's the second part. So you will basically get an end-to-end 3D protein structure generation program, and then we'll evaluate that using various means. I'm still working on the metrics. So one is, of course, you can just look at the structure, then compute the pairwise distances between them. So anyway, those details I'll put on the part two assignment. So, but you're good to go on part one right now. So because AlphaFold is a little bit more involved method, right? So this will be a group project. So you're allowed to work in groups of two, right? And I highly encourage you work in groups of two, no more than two. And so the idea is that you decide on your partners and email to me by tonight. So I need the group information by tonight. If you're not assigned to any group, then I'll randomly group you together. So by tonight, if I don't hear back, okay, I'll create two groups of students, and then you'll have to work with them. So talk to your peers, online, offline, and then send me that information by tonight. So that's the first milestone, is to send me the group information. So let me put that here. So this is the capstone project. So basically milestone 1 is 11th April, midnight. Okay, send group info before midnight. Okay, so that's that. So I will talk, in the light of what we want to do. So the only thing that's missing for us really is that the sidechain net, okay, sidechain net doesn't actually have the multiple sequence alignment for multiple sequences. That is, or rather I should say multiple clusters. So we do have, right, in the sidechain net data, we do have the evolutionary information, but we have it only for one cluster. So that means there's only one PSSM, right, the position specific scoring matrix. There's only one of those. And technically, we need many of those, or at least 20, 30, 50, whatever. So that I'll work on, okay? Because for that, what you have to do is you have to actually take every protein in the PDB, right? You have to then query the alignment databases, okay? Extract all the alignments, and then you have to group them into clusters and extract their position-specific scoring matrices. So that's a little bit involved work, and I'm looking for if there's a database out there. If someone has already done that, then we can just borrow from them. Okay, so I'm actually searching for that. But even without that, right, we can still actually implement the basic method. So you'll see how AlphaFold would do if you do not include multiple sequences, right? So even if you don't get to, let's say at least for part one, right, if you don't get to it I hope that by part 2 we'll have it. So within this coming week we'll have that information. So that should be an easy plug and play to the module, because the rest of the code will follow exactly the same information as the AlphaFold. So it should not be a big, and what we'll do is we will kind of mimic AlphaFold by kind of doing synthetic. When I say synthetic, I mean you'll actually generate a tensor, a 3D tensor, as opposed to a 2D information for the MSA. So your actual trunk will be the same as what's described in the AlphaFold method. Okay, so just a quick recap. So what are the inputs to AlphaFold? Okay, this is of course AlphaFold 2. So the inputs are the target sequence, right? So that's called the target, or the target feature. Okay, this is number of residues by 21. Okay, nres is the sequence length, right? Is the protein length. In terms of the number of residues, right? How many residues there are. The number of atoms can be much more, right? So n atoms is, if you want to do the full atomic, we will not do the full atomic, by the way. So that's another difference, is that when you implement this, you're only doing the backbone. You're only doing the carbon alpha. Okay. So n atoms is of course all the atoms. But we will actually be just doing this because we'll be predicting the C alpha X, Y, Z. By the end of part 2, that will be output basically, right? The X, Y, Z coordinates for every carbon alpha atom and there's only one carbon alpha per residue. So that's exactly the length of the protein. So that's going to be the output, final output. But that's the output of part 2. For part 1, it's just the same, the contact map. We'll evaluate part 1. So essentially, it will be a way to check how much benefit does the transformer give over the CNN, right? Because you already done in the previous. And by the way, I will also post my solution to the assignment, so you'll have access to that. So we can compare AlphaFold 2 with AlphaFold 1 on the same information. Same information being target, and we have the MSA information. So of course, so the MSA features, we will, like I said, we technically have this part. We have nres by 21, right? So that's our information because we just have a PSSM. Okay, so in part 2, so I'm just putting this in two steps. So for part 1 of the capstone, right, this is the information you will be using as input for now, because there's nothing else that we have. So the position specific scoring matrix is simply which amino acid is in which position with what probability, right? So we have one. So essentially, what that means is you take your target sequence, right, your input sequence, you compare with the database, right, and you extract one big MSA, and then from that one big MSA, you compress it all down to just this tensor, length by 21 tensor, probability of each amino acid in each position in the alignment, right? Now, so that's what we'll be using, right? So this is the input for part 1, and that's it. So and of course we can also use the residue index. This is just the actual position, right? So this is just the position info, which is just nres. Because we are doing cropping, we will be cropping the input sequence into chunks of 256 as inputs to the transformer. So you could have a longer protein, which you would have to then crop. So, but it's not a 2D crop like we did for AlphaFold 1. It's just a single crop, just a chunk, a contiguous chunk of 256 length, right? So anyway, this will also be the input to our model. So this is it. So these are 3 inputs to our model for the part 1. So this is our simplified AlphaFold inputs. Now, The actual AlphaFold has more, right? It has information coming from the template side. Template meaning that you find other similar structures like we talked about, right? So there is that information. So let's put this in red. This is the input for us, okay? So that's the input we will be using, which is comparable to AlphaFold 1, your implementation, again, simplified AlphaFold 1. So we can compare them directly to see how well we do with the transformer. Okay, now the actual AlphaFold, coming to that one, right? It has some extra information. It has the template. Template meaning the 3D similar structures. Or at least our best guess at that, right? So similarity is something that we can measure algorithmically. And some of those structures, you know, you kind of select the top 20 and then you sample from them. So they could be close or far apart. And you know, some of them are high quality, some of them are not so high quality. So they, anyway, that's that, and they also use the angles, right? So the template angles. So these are the template pair features. Okay, this we are not using for us. And when I describe the evoformer, I will actually not talk about this pipeline. But this pipeline is actually, you know, very similar to the other, meaning they will just add up into the final representation that we need. So I'm not going to talk more about this because we won't really be using this for us. And it's actually not that you know, different from the rest. It adds a little bit extra. So this is only if you have any structures that you have available. So the only thing we're actually missing is this part here, right? So the extra part here is n-clust. Okay. So this is what we don't have. So that's the problem. The problem is the sidechain net gives me only one PSSM, which is length by 21. And what I need is, right, multiple, if such information is available, I need multiple such clusters. So this part I'm searching, like I said, okay? So if I find a database that we can use, I will just refer you to that and you can download that data and you will have the full, at least, you know, set of inputs for our model. And of course, AlphaFold does a whole bunch of other things, but those are not that important, right? I mean, you know, if you want to win a competition, you need all those, but if you want to get to the 95% mark, you can get it with this much information. So we'll get to the 95% mark, hopefully, with this capstone. And if I don't have that, then we might not be that, well, you know, because the MSA information is very important in the prediction. Okay, anyway, that's the input. And remember what we do first is we transform them, right? So the first idea is that this is a raw input. And what you need to do is, which I'm not going to do in detail today because we did this in the last class, but to come back to the starting point, is that we need to take the raw features, right? So these are raw features or raw input, and we need to basically process them. So we have to basically convert them into standard, you know, dimensions, so that I can then use it for the evoformer trunk or the evoformer module. So what do we do? The first thing is that the target information, right? So you take the target. Okay, so that's the target, which is just nres by 21, right? And essentially you just do a linear projection, okay? So pass it through a linear layer, project it onto a CZ space, okay? CZ being 128. Okay, so we just project them to 128 dimensions. So our input features, so essentially this is just a very simple, right? linear neural, linear layer. You input is n raised by 21, output should be n raised by 128. So this is going to give me, okay, n raised by 128, and this gives me n raised by 128. Okay, so we call this AI and BJ, okay? So every row here is AI, every row here is BJ. I'm just using two different indices, but essentially it's the same length, right? N by 128, N by 128. Okay, now all you do is you do an outer sum, right? Just like it's like you're creating a feature, your pairwise feature. So essentially, you basically we can do more, right? We can of course concatenate them with the difference and the element-wise product if you need to. But if you just want to stick with what AlphaFold does, is that we just do an outer sum, right? So outer sum is your Zij now. Okay, so this gives us something called Zij, which is simply AI plus Bj for all I for all j. Okay. So that's your 128 dimensional pairwise feature. So Zij. So this basically now gives me a n by n, right? So it's n res by n res by 128. Clear, right? So that's this is called the pairwise representation. Okay, so this is the pairwise input. Okay. We are not done completely with this because to this we will add a relative position information. So we basically, so what we do then is we combine this with the, so we take the pair representation. So Zij is basically Zij plus relative position Pij. Okay. And what is Pij? Well, Pij is Pij is simply let's see here. So this is the positional difference, right? So what you do is you basically take I and j, right? So you basically look at the index for I minus the index for j, okay? And then you basically bin into minus 32, minus 31, 31, and 32. Okay, one hot. So the idea is that you figure out how far apart they are, like I said, right? So this is basically measuring distance up to 32 to the left and 32 to the right. So does I come before j or does I come after j? And how many positions before, how many positions after, right? Or this is before and that's after. And then whatever that distance is, right, you discretize it into this and you create a one hot. So you say, am I after you or before you? And which index am I in, right? So that's the one hot part of this. So, and then you do a linear projection on that. So basically that's what RelPos is. So RelPos is simply a linear one hot of Dij, with this is Dij. Okay. Okay, so that's just the relative position information, and this one. Let me see one thing here. So that's yeah. So this linear will of course project it back to the 128 dimensional space, right? So let me just confirm that relative position. Yes, okay. So actually, I should have just said, I should have just, gotten rid of this. I should have just said plus Pij, just to be clear. So it's a vector, right? And that Pij is this. So I mean, but this module is called relative position. So that's what it is. This is the relative position module. Okay, and Pij also belongs to RCZ. Okay, so it all makes sense. Basically, we're just doing, like I said, one hot coding followed by embedding, right? So essentially, taking that, you're creating an embedding for that one hot vector of distances or difference of the distances. Okay, so we got that. So that takes care of the pairwise. So this is the final pairwise representation is this one, right? So it includes, this is the final pairwise representation. Okay, so that's one of the inputs, and then the other input is this part is the one where we are lacking the one of the dimension that we'll see. So the input, right, technically should be n class by n res by 21. So this is the MSA features. So this is the MSA. So um, the MSA representation. Okay, so the MSA representation, the input is, it's actually n clust by n res by let's say at least 21, or they technically have more features. Okay, that's the input. So what we want to do is we want to transform this into a n clust by. So this is what we need for the output. N res n clust by Cm, where Cm is 256. Okay, so essentially I want to project from a 21 dimensional feature input to a 256 dimensional input along the third axis, right? The feature axis. Number of MSA clusters and the sequence length remain the same, right? So this sequence length is determined by your input sequence. Right now, the way we have it, we're going to have just one row here. So n class will be equal to 1. Okay, just keep that in mind, that if I don't have multiple clusters, then there's only n class equal to 1. So for us, as it is now, n clust equal to 1 for now. Because I'm searching. All right, so now, but regardless, right? Uh, we can, like I said, so this was the part I was saying, that your raw input, n class will be equal to 1, right? But I can actually generate whatever size output you want, right? It's just like you do linear projections after linear projections, right? So essentially, if it's almost like we have, several filters, if you will, right? So if I do one linear layer, right, I can. So here's the. I guess, okay. This is the actual, right? This is the actual, say, AlphaFold, right? So this is what actual AlphaFold will do. Okay. So what will we do, right? Okay. For us, like I said, our input is just this. Okay, because n clust is 1. Okay, so if I don't find other MSAs, right, this is all the input you have, which is n res by 21, right? So this guy, I can actually do one linear transformation, right? And I can get my 256. Okay, so here's what I'll do. So essentially think of this as multiple, okay, linear transformations. So for the first one, I can obviously transform this into, let's keep it the same, right? So it will be n res by 256, yes? The second one, I can do the same thing, right? So I do another linear projection. and I can create another 256, and I can do as many as I need to, right? There's no problem. Okay, so then I can combine these all together, just stack them, right? And I will actually get a 3D tensor. So this is what I want you to do. Okay, in the absence of, this will be my nclust nres 256, okay? So this is basically nclust linear layers. Okay, so we are basically making up our own, fake learnable MSS, okay, for whatever it's worth, so that the input going into the UO format will always be the same. So that if we do find something, then you simply get rid of this, right, and you replace it with a normal single layer, and your input will be just like in the AlphaFold. So anyway, this is so that now the reason I'm doing this is because, as we'll see, one of the key innovations or one of the key effective methods in the AlphaFold 2 is that they do the position wise, like the pair wise attention, but they also do sequence wise attention, right? So one sequence looks at the information from another sequence. So if I don't have this dimension, then there is nothing to, there is no attention that I can pay to anybody else along the sequence axis. So at least, you'll get to implement the whole thing. Now, whether it will be actually any use, we don't know, but let's see. Okay, so one more thing here is that this part is easy, right? So just projecting it from here to here is just a linear layer, right? So this is just a linear layer. But they also add the pairwise information from the. So what they do is they will simply add the pairwise. Let's see, how was it? Where did it go? Yes. So what you do is not the pairwise from the target information. So here's what you do. So there's one extra step here. So this, by the way, this is called M. So this each entry here is called MSI. Okay. And so MSI is a vector which is 256. Okay. So sequence S and position I. Right. So just like Zij, right, is basically I versus J. So that's the convention we are following, that I and J refer to positions in the protein, okay? And S refers to a sequence ID in the nclust dimension. I refers to a position in the number of residue axis. So obviously, you got MSI coming in and you got MSI going out, right? Or whatever the input is, right? You're going to say the pairwise information comes in, but this is the final, or before we do the one more step on this. So MSI is simply a linear projection of from 21 dimensions to 256 dimensions. That's all. So just a linear layer is all we need. Okay, so now before we, so now what do we do? So now we have the same thing here, right? So we have MSI for us. So all you have to do now is combine the MSI, okay, plus MSI plus basically it will be what we say a linear. So let me do it graphically here. So here's what I want to do. So what I want to do is I want to take my MSI and actually no, let them draw the MSI a little bit below. Okay, so I take my target. Okay, so again the target. Okay, target is nres by 21. Okay, first I project this to what I call CI, okay, which would be 128. Oh no, this time it has to be 256 to match the MSA, okay. So this is nres. Okay, so you see, I'm doing the same projection that I did for the, just to back up here, right? So initially, when you created the pairwise representation, you just project AI and BJ, and then you do outer sum. This was in 128 dimensional space. So now what we do is we do another, a third linear on the target information, which is just the one hot and the one hot input encoding for the sequence. But you project it into 256 dimensional space, and now I simply add them together. So this is going to be the final thing. So the MSI is going to be MSI, where are we? Okay. MSI is right. So the MSI, so your new MSI is simply the old MSI, which is coming from here, plus CI. Okay. Does that make sense? So basically, right, it's like there is no S index here, right? So that means it is the same position being added to all the layers. So graphically, this means that you take your MSI, right, plus you basically, right, add in, this is the I dimension. So, right, you add in the I by, 256, right? And you do it like a stack of this conceptually, right, n plus times. So graphically, that's what it looks like, because I have only one, right? I have only one output here. Number of residues by 256 is the output, right? And I'm basically adding the same thing for all the S's, because S is a free parameter here, meaning S is the freedom that you have. So S, you basically, for every row, you basically add the entire plane to this. But mathematically, it's as simple as this, right? This will simply distribute. And actually, this is actually already in the right dimension. This is 256, this is 256. So it's actually fairly straightforward. So that's the final. So this is the final MSA representation. Okay, so now we are ready for the evoformer block. So these are going to be the two inputs for the so this is the MSA representation. Okay, so now we have everything we need for the evoformer block. So let's talk about the evoformer block. So the evoformer now, this is the actual thing you're obviously implementing the whole thing, but so the evoformer trunk, what it will do is it will basically process these two inputs and create the output that we need. So the inputs to the evoformer trunk are the pair representation, Zij, okay, and the MSA representation. So basically two three-dimensional tensors. This is nres by nres by 128. This is nclust by nres by 256. Okay, this is MSI. All right, so that's the input to the evoformer. So now comes the issue of the attention and the axial attention, right? So that's what's going to be happening on this one first. So I'm going to take the MSA representation. So just to define, this is the pairwise representation or the pair rep, and this is the MSA rep. Okay, so these are two tensors that get into the evoformer. So let's see first what happens to MSA rep. So the MSA rep is the axial attention. Okay, so what we'll do for the MSA rep is we take this and we do what is known as axial attention, which means it's going to be row and column wise, okay, alternating. Okay, so that's happening on the MSA side. That information will then be somehow combined with the pair representation, but then the pair representation, after you look at some information coming from this side, so you kind of do the MSA axial attention first, you combine it with the pair representation, And now on the pair representation, you do something else. Okay, so here you do what is known as triangular attention. And then you do multiplicative attention. And you do a third thing, which is the what is it? Triangular multiplicative. One sec. Oh yeah, no, that's it. You do two things, but you do it kind of like incoming and outgoing. Okay, so technically there are four things happening based on like the directionality. Okay, we'll discuss that what the directionality means. But those are basically the two types of updates that are happening here. Okay, so as I said, let's start with the axial attention first. So what's happening in the axial attention? Okay, so here's your first evoformer block. Okay, so first you take your, so this is the first part, which is row wise attention. Okay, uh, it will be gated like we had briefly mentioned last time, and it will also be pair bias. Meaning, pair bias simply means that the pair representation, right, will introduce something called, it will introduce a bias term into our equation, which will become very obvious once we have the equation written out. Gated means that we'll have something like a LSTM type, gate. Just, I mean, it's a much simpler, it's just a sigmoid gate, which will simply control, how much information we read in and read out of the, so if it's useful, we use it. If it's not useful, we don't, so that gate will control how much information is being used. So what's the input? This is working on the MSA rep, okay? So that's your input. So to this module comes in the nclust by nres by 256, right? So that's your MSI. Okay, so what we want to do here is we are going to so row wise, right? So row wise means it's a little bit, the term is a little bit confusing because we'll see when I say row wise, what I mean is, pick a sequence, okay? Pick a sequence and then do attention over the positions, okay? So now you could argue whether, right? So why is it being called row wise, right? So I think there's a little bit of a confusing terminology because technically, I mean, I see why they did it, right? Because it's actually the rows of the tensor, right? So you're applying attention on a row by row basis, right? So it kind of makes sense as row wise. But on the other hand, it's actually over this axis where the attention is, okay? You're actually computing the attention between the pairs of positions. But then you sum it across all the sequences. So again, if it were the other way, then maybe I would be confused that why are they calling it that way, right? So one can always pick like so, but as long as we are clear what's happening, we're good, right? So let's call this still row wise, or I should say row specific. Maybe that would be a better name, right? That is happening on a row by row. So S is fixed, okay? So first I pick an S because that's what I'll sum over in the end, okay? Because I'm going to concatenate across all the rows. Okay, so here's what happened in the so let's just say right now for all S, right? Okay, so that's the outer loop. Okay, so now when I say for all S, right? So this is belonging to 1 through nclust. Okay, but now I've got a particular S, right? So I've picked one of those. So now let's talk what happens for that one S. Okay, so if you pick an S, what does that mean? So that's like you're picking a slice of this, like I said, you just pick a slice, okay? That's one particular S. Okay, so now for that particular S, what is the information? I just take this out and I'm going to draw it here, right? I just have nres by 256 is my. So I've taken that flat thing and I've made it just n raised by 256, right? That's the, so for a given s. So s is fixed, so let's call that s here, right? So s is always hanging around over our heads. So whatever I talk about is in the context of that one s that I've just selected. So this is now a pure, it's very simple, it's just actually a pure attention. So what I need to do is, well, I should write it the other way around, I'm sorry, so that, because I want to do the row attention, right? So just to be clear, I oriented it this way. So this way I can do row, so that each row of this, right, is what I'll transform. Okay. So I took that, which is this is the nres by 256, right? So I'm just drawing it out this way. So one slice of that. So what do? We do the basic attention. So pick a row from here, right? And basically create three projections, right? The query I, the key I, and the value I. Okay. So this row, what shall we call it? So this is technically, well, technically it's actually m. Technically it is ms, right? So if you think about it this way, this is the ms. If I say for all I, right, that's what this is. So this is so technically this is ms. Right? So over all I, right? So if I look at all the I's are going here. So technically this row is actually MSI. Does that make sense? Right? It's still MSI, right? This single row. Because if you think of what MSI is, actually it's a vector along that axis, right? So I can actually refer to it actually as MSI. So that way we keep a consistent terminology. So this technically is actually MSI. Just redrawn because I'm focusing on only one S for now. So S you can ignore, right? So I could have just called this MI, but to be clear, it is actually MSI, right? Because S is fixed, and now all the I's range from 1 through n res. So you take this MSI for a fixed S that is, right? And then you just create these three queries. So now, technically speaking, I should probably add a superscript here, right? Because we're going to do this for each S subsequently. But let's not worry about that, okay? This is what keeps it clean, right? All I need to do is I've got a MS matrix that comes in. Each row of that matrix is called MSI, which is the same MSI in the original tensor, so there's no difference. But I'm ignoring the S in the sense that it's fixed for now, right? Because it's for all S. And so what I need to do is just take this this vector, which is 256 dimensional, and project it into my projection space. So take a 256 dimensional vector and project it. And here dk is 32, and the number of heads is 8. Okay, so this is a pure attention, transformer-based attention that we know of. Okay, so what do we do with this information? Well, you do the standard stuff. So what you want to do with this is first you want to create the query key pairs, right? And that will be your attention. So this will be the row wise. Yeah. So here's what we'll do. So you take your query I, right? Transpose key j, right? You divide by root dk. Okay. So I want to basically compute the attention aij is softmax. Okay. So this part, right? If I were to stop here, this would be standard attention, right? Of course, you can write this in matrix terms, right? But it's easier to see this for a pairwise what's happening. Then you can translate them into matrix equations later. So this is all happening, right? And just to emphasize, right, this is all happening in the context of a given S, right? So just so that we know. So one sequence has been, one plane has been chosen, and I'm just doing things on that plane. Okay, so I just need to now add what is called as the pair bias. Okay, so this attention, we're going to add a bias term. Okay, so bias, as you know, is a scalar, right? And so now whatever the dot product was, which is also a scalar, by the way, I add a bias term. This bias term comes from the pair information. Okay, so this bias term comes from pair information. Okay, so comes from the it comes from just a linear of Zij. Okay, so all we are doing is we are taking the input from the pairwise input, right? Doing a linear transformation on that and getting a Bij. So in matrix terms, right, the input here technically is also this vector, right, which is nres by nres by 128, which is Zij, okay, and we're basically mapping it to just a nres by nres to get Bij. And Bij is a single scalar, okay, so this is just exactly as it is. So Bij is a single scalar. So I just have a linear layer, right? So it maps from 128 dimensions to a single dimension. Okay? You see what I did? I basically just compress all the information from that 128 dimensions onto a single scalar. So that's just, so you can do this like, in terms of tensor operations, you'll just do a linear layer on that tensor to get a B tensor, right? So if this is a Z tensor, this is a B tensor. So if I call this big thing, if I call this Z, okay, which is a 3D tensor, nres by nres by 128. This tensor is a B tensor, okay, which is just a nres by nres. So how did I go from here to here? Well, this has to obviously map to 1, right? So that's just a linear. I mean, I don't have to preserve that one dimension, right? Because when you do the linear layer, you simply map it to 1 and then you can squeeze it out if you want, right? So, or unsqueeze it. So that's the point, okay? So that's just a linear is all we need. And linear means that you're doing weight vector and bias. These linear, by the way, are without any bias, okay? So just to be clear, like when you do attention, you don't have any bias. So when you project it down, these are all linear transformation into 32 dimensional space, right? So you go from 256 dimensions to 32 dimensions. So these are all just linear, no bias. So bias is just, the offset, right? So when you're projecting it down to a low dimensional space for attention, you don't really add bias to it, which you probably saw in my code also when we did the BERT model, right? For the attention, the core attention, the self attention part, I used the linear with bias equal to false parameter. Anyway, so that's easy to do. So everything clear now? So I got my attention, right? So I got the MSA rep for a given sequence. I first compute the attention in this space, and then I add a bias from the pair representation. So that's your attention for the different positions. All right, and now you just have to add a gate after this. Okay, so so the idea is that I need to now compute my. Oh, by the way, one more thing. This is all happening with the heads, right? So I'm just showing you for a single head, right? So not to confuse you. So technically, there are 8 heads. So there's also a superscript. So there are 2 superscripts hovering here, right? So one is S, right? Which sequence am I talking about? That's even before the heads come into play. And then, of course, for every one of these, there is a corresponding head, right? So QI1, QI2, QI8, right? Key 1 through 8, value 1 through 8, right? So there are 2. So just to be clear, there are, right? This is so 1 per head, right? So this is 1 per head. So I could have said that essentially there are two so better way to describe it would be, right, cross H, right? That's easy way to say that. And then this would be also cross H, okay? So for a given sequence, for one sequence, there are attentions, and this whole plane is cross H, okay? So that means there is Aij head 1, Aij head 2, and so on. And in terms of matrices, you can think of this as the A matrices, right? There are actually 8 different A matrices, right? So this is just showing you what happens to each element of that matrix. So, so this is technically just A, right? And this is cross H, okay? So the attention matrix, which is nres by nres, and this whole thing is cross S, right? Meaning, when I say cross S means, actually let's just say for a fixed S, but you'll do it for all the S's, of course, right? So let's put the S here. So that means for a given sequence, I can get 8 different A matrices. Each of those is the nres by nres. So, these equations are good to understand what's happening, but when you implement this, you are not going to do this in a pairwise manner, right? If you do this in a pairwise manner, it will take you a month to compute, right? You will have to think in terms of the actual tensors, right? All operations must be happening on tensors. So technically, you have to create these matrices, the Z matrix, the B matrix, right? The A matrix, or and the corresponding tensors, So, Z the tensor, B the matrix, right? A the matrix, and so on and so forth. But anyway, they're 2D, 3D tensors, whatever the dimensionality is. So, you better be writing your code in terms of tensors. But this makes it clear so that you can always go back and check, that did you do the right thing, right? So if you compute those elements and then say whether your A matrix with the tensor operation matches that, then you're good, right? So it's good to kind of do a sanity check of your code. If you're getting the same numbers using the pairwise approach, it's good during testing. You can spend some time on a small data set, right? No problem. So that way you can debug your code and make sure that the correct operation is being done. That's very important. Okay, so what have we done, right? So essentially, right? So what is the intuition here? The intuition, again, like I said, is that for each sequence, right? So think of it this way: evolutionary speaking, there are multiple sequences that are similar to my input, right? So I'm saying, okay, if there are these multiple clusters or multiple sequences that are similar, then let's look at one of them at a time and figure out what are the pairwise dependencies, right? So in terms of the different positions of my amino acid, of my protein, okay, how much does position I depend on position J? Those are all the attentions I've just computed. Okay, so now that I have all the attentions, now I'm going to create my new representation. And before I do that, I just add a gate. So I say, okay, here's my output. So the output for, let's just say output for OI, right? So this would be, again, for a given head and for a given sequence, right? But right now, just playing along with the single head and a single, fixed sequence S. This will be just GI, okay, times this now over all J, attention Aij, and now you use your value J, right? So this part is again that same equation. So this equation is the A times V part, right? And this equation is the G element-wise with that. So G acts like a gate, okay? So this is the element-wise operation. Okay, so GI is a gate. Okay, so this is a gate. So this part is your standard attention. So take your value vectors, right, in that projected dimension. So you're just saying that how much attention does J pay to I, right, position I. Then look at the value representation for the jth index and combine it in proportion to its attention, right? And then sum over all the j. So if I sum out the j, then I'm left with the I. So I know now what my output vector looks like for the I. But instead of taking the attention directly, you add a gate. This gate is a sigmoid, so it's a value between 0 and 1. So it's just saying, how much should I be, so if it's 1, the whole information passes through. If it's 0, the entire information is basically discarded. If it's somewhere in between, but this is a learnable gate. The network figures out how much of this is really important, right? So the gate, how do you compute the gate? Well, just a sigmoid. So GI is simply sigmoid on MSI, right? So so, and this is just a single scalar, right? This is just a value between 0 and 1. Now, this is a 128 dimensional vector, but mathematically that's great, that's easy, right? So all I'm saying is that, right, take that 128 dimensional vector and essentially you basically put the output to a single neuron, right? And that single neuron then you apply to sigmoid on it. So sorry, actually, so then it has to be linear here, otherwise it will not work. Okay, so what that means is take your 256 dimensional vector, map it down to a single neuron, and then apply a sigmoid, right? So that's what GI is. So this is the linear part. So I think, as I said, this equation makes it crystal clear what's happening. You just have to translate these into the tensor forms when you actually implement them. But you can check these using the the individual element-wise thing. Okay, and now this is happening per head and for each S. Okay, so I basically have one output vector, right, per S per head. Okay, so now all we do is concatenate them all together. So now a final MSI tilde, meaning the MSA rep. Okay, so how do I update the MSA rep? This is simply going to be a linear layer, and now all I have to do is concat all the OI for all the heads for all the sequences. Okay, so you see what we did? We take these are 32 dimensional vectors, right? So each OI is a 32 dimensional vector, right? Because your projection is 32 DK, okay, across all three. So when I combine this OI is actually a 32 dimensional vector, okay? So now what do we have? So first you do 32 times 8, which is actually 256, and then you do it across, times S, which is now n-classed by 256, okay? Now you take the n-class by 256 and you do a linear projection onto that, right? And so the final thing should again be what? 256. So this is the final output. So you're going from n-class by 256 to 256. That's what the linear layer will accomplish. Right? So concatenate all the heads over all the sequences, and then do a linear projection on that. Does that make sense? Because the index I is right. So this is what n rests, right? So this will be actually one thing. So yeah, well actually you'll probably have to. What is the best way of doing that? I'm thinking. So for each sequence, you can. Well, now you have to start thinking in terms of tensor, right? So when you implement this, there'll still be a little bit of inference you have to do. So how will you best organize this information, right? So I'm trying to think out. So since I have multiple heads, that gives me 256, and then I have, yeah. So technically you can organize this. Um, okay. No, I take that back, right? So this is actually a fixed. So this is okay. My mistake. So this is a fixed S, right, for the time being, right? So, so, so in this equation, right, I mean, there is a S hovering around, but it's not times S because you're not summarizing information from across. This is for a fixed S, okay? Fixed S. So the variable here is actually I, right? And so this makes sense, right? So there are actually only 8 things. So, sorry, this was, yeah. So one has to be clear about interpreting it correctly. So that's what it is. So you're going from, okay? Okay. So this makes sense. So essentially, yeah. So essentially what's happening is, right, so for a fixed S, right, I need to update the vector, right? But this I position has been split into 8 heads, right? So I'm concatenating. So this is exactly actually like the attention, like the output layer of the attention, right? So the final, like what you do is you concatenate all the heads together, and then you just do a linear projection, okay? So that's what we're doing here. And then you repeat it for all, each one of the S. So technically I can do this whole thing in one big tensor operation, but the simple way is to do like a for loop, which, I mean, you're not going to implement it that way, but I'm just saying, right, you could do it for every S, right, for all S. But the whole thing can actually be done in a completely tensorized way, which is what you should do, or you should endeavor to do that when you implement. So first you can do a for loop to see everything works, and then you can, verify your results this way. Okay, so is this clear? So this is what is called as the row attention. Okay, so what did we do? There is so basically, the simple thing is really the same attention we've been talking about, right? There's a query, key, and value, right? If I ignore everything else, right? Then if I ignore this, that's query key, right? And then if I ignore the gate information, then it's only the same thing, right? You combine all the values, right? You concatenate all the heads, and you get your final thing, right? Attention, pure attention, okay? So I mean, it might look a little bit more confusing here, the way I described it, but it's exactly what we did for BERT, okay? There's no difference for that part, right? So the only extra elements here are, there is a bias term being introduced here when you do the attention, right? So that's like saying that, compute the, when you do the Q K transpose vector, right? You add the B or the tensor, add a B tensor to it, okay? So add a B tensor, and then you get your A matrix out, okay, which is the attention matrix. So that's the only change for the A. Now I've got the A. And then the final change is that when you're computing A times V, right, you multiply by the G matrix, okay? That's it. And then you get your outputs and you concatenate them all together. So that's the only real difference here. So it should be hopefully easy to just think along those terms and implement it that way. Was there any question? Yeah. You technically don't, but it's always good to have it because this is, what if I want to change the number of heads, right? If I want to make my heads 12, then you would need a linear to project it back. But here you don't really need it, but it's just for good measure. And also, technically speaking, right, the point is that, yes, it is 256, but they are actually 8 different heads, and they've just been concatenated, right? So the idea is that, in fact, you need it in some sense because you want to combine that information into one final. So instead of having like 8 separate smaller pieces, I want to say, let's just manipulate that into the final 256 dimension that I need. Okay, so that's your row. Okay, so let's take a break there because the column would be easy now. Now that we know how to do the rows, the columns are going to be exactly this, but now everything is going to be flipped. So instead of the attention over the ij, it will be over the s and t, like the different sequences. Okay, but everything else actually remains the same. So it'll be easy to kind of explain that. Okay, so break and then we'll begin. And let's circulate this attendance sheet. And remember again, just so that a few people who came late, I need your groups of 2 for the capstone project. I need them by tonight. Okay, so all the group information should be emailed to me by tonight. If I don't have group information by tonight, I will randomly assign you in groups. And I figured out exactly the tensor operation you have to do, right? So I'm going to try to give my best shot at the tensor thing. So this way, at least you'll know what to implement for this one. Okay, so this is the tensor version of what I just said. Okay, so tensor version of row-wise. Okay, so here's what we're going to do. We got two pieces of information. So one is the pairwise, right? Which is nres by nres by 128, right? I'm going to call this a Z matrix, okay? The basic pairwise matrix, right? The pairwise. This is actually very straightforward. You just do a linear, okay? And you just get an nres by nres output. I'm going to call this matrix B. Okay, they correspond exactly to the lowercase terms, okay? So this matrix is just nres by nres by 1, if you want, just a scalar, right? So I'm going from 128 dimensions to a 1 dimension, right? So this is the bias matrix. Okay, so that's all you do here. Then you take your MSA, which is n plus by nres by 256, okay? So what you do here is you are going to, all right, so here's what you're going to do. It's still not completely, because I'm still using, I'm not doing so I'm basically extracting for a given, I'm going to show you for a given S, and then you can generalize this because then I have to think even more, which I'm trying to do it on the fly. But here's what you're going to do. Okay, so pick a S, right? Like I said, so for each S, I'm just going to call this MS, okay? So there's the M matrix, okay, which is now nres by 256, okay? So that's what this is. Okay, so now what I do is I now do QSH, KSH, and VSH, right? So H, remember, goes from 1 through 8, and S is, of course, fixed, right? So for a given, so that's what this is. So I get the query, the key, and the value. These are all basically matrices in 32-dimensional space. Okay, so this is the Q, the K, and the V. Okay, so now I need to compute the attention, right? So the attention is easy. So attention SH is simply Q SH query SH transpose over root dk plus B. Okay. Now you can see that the dimensions all add up because the query, right, is nres by 32. You times that with the transpose of the key, which is 32 by nres. So this is the k sh transpose. So you get nres by nres, and B is all B is already, as we see, nres by nres, so it all checks out. Okay, so attention should be the attention should be a matrix of this dimensionality. So that works out fine. Oh, and there is a softmax, of course, right? And softmax along the rows. Okay, make sure it is along the rows. Okay, so that's the attention matrix. And now all you have to do is, right, compute OSH, which is going to be GS element wise with GS with ASH times VSH. Okay. So this is a gate, and then you're going to and O is simply then going to be concat OSH along. So this is OS. Okay. And then you're going to do a linear on top of that. Okay. and this is actually your MS. Okay, that's it. So in matrix terms, and what is G? G is a gate that we apply. So G is computed this way. So you take your so I'll give you the full what GS is. So I'll give you the complete G matrix actually. So this is n clust by n res by 256. Okay. So this is your complete M matrix, right? Not even restricted to a specific S. So you take this first, you do a linear, and I get a n clust by n res. And actually, technically, this should just be a vector. I'll explain why. And then you basically do sigmoid on this. And so this will give me a n clust by n res matrix G. Okay. Okay. And what is GS? GS is one row of this matrix. Okay. So each row, like this row here, is a GS vector belonging to n res. Okay. So GS is a vector. So essentially, you see what's happening is that if you think about this matrix, right? This matrix is going to be n res by 32 matrix. Okay, the product of the attention and the values. Okay, is an n res by 32 matrix, and you're multiplying that by a vector. Okay, so this vector, like the row of G, is controlling, which row. So it's actually applying on a row by row. So each gate applies on that row. Okay, so that's why I just need a vector here. Okay, so hopefully anyway, you can go and parse this, but I think this is the right. So the only shortcut I did is I did not do I didn't do the S part, right? Because then you have to do a tensor of attention, which which I think we can figure it out, but I don't want to do it right now on the fly. Okay, so anyway, that's that, right? So at least we have a little bit better, at least computationally. Okay, so we've just done one part. Now comes the second part of the EO former. So actually, once you implement it, this will become, it's actually not that complex, really. I mean, it looks a lot more complex than it is. But it's really, it's a different play on the attention at each time. And so I believe that once you get the one of these blocks right, the rest will follow. Okay, now let's do column-wise attention. And this is simply gated. There is no pair bias here. Okay, so the idea here is that you again take your M matrix, right? So this is again happening on the MSA representation. Okay, but now it's column-wise, right? So what column-wise means is focus on one column at a time, okay? So if I pick a column, then the variable becomes S and T, like two different sequences from my cluster, okay? So now I will be fixed. Previously, S was fixed, now I will be fixed, okay? Meaning I'll do it for all the I's, but I will be fixed, so I'm going to pick a slice like this. Let's do it in red. Okay. So basically, fix an I. Okay. So now it's column, right? So I've got a column now. So now you get the attention between S and T. Okay, two different sequences. So how do the different sequences affect each other? So basically, we have to say fix, or I should say for all I, right? 1 through n res. Now everything happens inside that, right? So we fix that, and now we do attention. So it's basically attention over the sequences in n clust, right? Meaning from 1 through n clust. So the same logic applies. It's exactly really the same information, which is so what I'm going to do now is I'm going to pick that slice, right? So that slice now, okay, is going to be n clust by 256, right, as opposed to and res. And now it's easy, basically, right? No big deal. Basically, for any given s, right? Compute the for any given right. So yeah, compute the OS, right? Not OS, like QS, KS, or I should say, if I think in terms of matrix terms and value I, right? So I'm computing the entire matrix, right? But if you want to do it pairwise, let's do it pairwise. Like I said, it's always good to go back and do it from a pairwise perspective and then generalize it to the matrix, because then it's easy to think of what we're doing. So essentially what I want is, for any given row of this matrix, right, I want a query S, a key S, and a value S, okay? Look at the difference here, right? This one was, if I go back, Qi, Ki, Vi, you see? This was over the n-res dimension. Now it's the same thing, but now it's over the sequences. So technically I could call it I, but we want to keep it that these are over the sequence, S. So instead of saying Ij, right, how much does J pay attention to I'll say how much does T pay attention to S, okay? So this, another row of this matrix will be called T. Okay, so attention works exactly the same. So here's what the attention will be. So we can say let's see, what is the S and T, right? So what we want to do is, I want to find out the attention between S and T will be softmax. Okay, so it will be query S, right, dot product with the key for T, okay, the K for T, over root dk. That's it. And the dimensions, I believe, are the same. Yep, it's the dk. By the way, they call it C here, okay? So don't get confused, just to be clear. I use dk to kind of match the bird, but they use the symbol C, okay? So C is 32 for the projection. So here the same thing, okay? So these are being projected into C space, which is 32 dimensional space, projection dimension, and h equal to 8. Okay, so let's not call it dk. To be consistent with the paper, so it's root C, okay? So I got that, and then I do a gate. So now again, the issue is that, oh, by the way, and then there are the different heads, right? So this whole thing cross H, okay? So the whole thing cross H. So for the different heads, yeah. No, so this time we don't add a bias. I mean, why? I guess, well, actually, yeah. The reason we don't have a bias here is because, right, we had a bias that was coming from the pair representation, right? That was the IJ bias. Here we don't have any counterpart, right? So since I have my n plus by n res as the input, technically I would need a n plus by n plus bias. But where am I going to get that from, right? I don't have that information. So they don't have any bias here. But that's a good question, right? So no bias, and then we just add a gate. Okay, so the gate would be the same thing after that. So the column thing then is O of, this is going to be O of S, okay, is going to be G of S, I should say G of, I guess it should technically be G coming from the I, okay. I'll have to, and then G, what did I do here? One second, I want to keep it consistent with what I did here. So the pairwise was G, yeah, OS, so GS, sorry, GS. Oh yeah, so it makes sense, of course. GS, element wise, and this is going to be sum over all T, AST, VT. Okay? And then this is, of course, happening over the heads. And then finally, you get your, updated MSI again, is now basically going to be linear, concat, O of S by H. Okay. So it's exactly the same. Okay. There is a gate. So it is still gated, but without a bias. But it's exactly the same. So whatever you do, just so technically you actually just have to write the same piece of code because you see, I mean, I'm calling it SNT, right? But implementation wise, it makes no difference, right? I'm just going to give you a matrix, right? The matrix will be some n by some dimension, okay? And you might as well just call it I and J. It makes no difference, right? I mean, as long as you give it the right matrix, it will do the right thing. So it's technically they both can share the same code, meaning the same. It'll be independent parameters, of course. So, but it'll be just replicate that, but with a new input matrix. That's all. So it's actually implementing this is once you get the row, the column is pretty much straightforward. Okay, so I got the row, I got the column, right? So at this point, we are done with the MSA part. Okay, there's only one step which we'll use for the, like in terms of the grand scheme of things, right? So see what we had here, right? So from the MSA representation, which was what I'm calling the M matrix, I'm calling this the Z matrix, right? So the M matrix or the M tensor, uh, we did the axial attention. Okay, we did one row with one column. Okay, so you just do one row and one column, and now I need to take the information from the final M and pass it on to the pairwise. Okay, and now I have to then manipulate my pairwise representation. So here's what's going to happen at this point. So what we do then is we take our M as it is. So here's what we did. So just to recap, here's your input M, right? I do row wise and I get a new M. Then I do column attention and I get a new M. Okay? So that's all we have done so far, right? So two blocks, row attention, column attention. Okay, so this is, dimensions are exactly the same. So this is the updated M at each time. Okay, so this is still n classed by n res by 256. Okay, so that's our, what the picture looks like after the row and column attention. Together they make up the axial attention, okay? Okay, so what they do is they have something called a transition network, which is again, just, the transition is just a linear network, okay? So the transition network, what it does is, so let's put it here, transition. Okay, so what is transition? Before I do the transition, let me just tell you that now you get the final M that I'll be using. So this is again, you just update the M matrix. Okay, this transition is like normally in any kind of a network, right? After you do a few operations like convolutions or attention, you need to throw in a few linear layers, right? So that's what transition will do. It's just a linear, relu, linear. Okay, that's what this is. So transition basically is, transition is exactly, it's, so it is, and they're doing a little bit of, yeah, so what they're doing is, here's what they did, okay. So this is technically 256, right? But let's call it CM, right? Which is, of course, 256 going in. So all of this is all in CM space, right? Okay. The final thing will also be CM, okay? But in the transition, they will project up, do the ReLU, and then project down, okay? So what does transition do? So first you take, you do linear, okay? And this linear will basically map CM to 4 times CM, okay? So that you do first linear on the input tensor, right? So this tensor remains the same, meaning CM goes in, right? And 4 CM comes out. Okay, that's the first linear layer. Okay. Then you do ReLU. Okay. So that still remains 4 CM. And now you map it back. So you do linear 4 CM to CM. Okay, so out comes CM along the third, So the rest of the dimensions are preserved. I'm only showing you what happens to the feature dimension, right? So it's really two linears with a ReLU in between. They probably also have a dropout somewhere in there, right? So you basically do the, and they probably even have some, I have to check. They're probably some layer norms and bash norms somewhere in this picture, right? So dropouts and bash norms are kind of spurs. We can look at the actual details when that happens. So that's what transition does. Okay, so transition network is just like I say, a fully, just linear layer with some non-linearity in between. So this is their definition of what transition does. Okay, so that's exactly what's happening. So that's very simple. So now you have the final MSA information. So now what do we do next is we have to start manipulating the pairwise. So now we come to Z, okay, which is nres by nres by CZ. Okay, CZ is 128. Okay, before they do anything, right, they want to take, so the idea is to, make the information go back and forth between the MSA and the Z, between the M and the Z, right? So remember, for the row-wise, we already use the pairwise information as a bias. Now, what I'll do is I'll construct a new, you might say, update of Z using the MSA, using the MSA information, using the row and the column axial attention. So what I do is it's called the outer product mean, okay? So the idea is to do, so this will be combined with outer product mean coming from the M matrix or the M tensor, okay? So in other words, this M tensor, as you know, it is n clust by nres by Cm, right? After doing all the transitions and everything. If we want to combine it with this, the dimensions do not match, right? I mean, that's nres by nres, this is n clust by nres, right? So what I must do here is to look at, somehow take the nres dimension, right? And create a pairwise, like nres by nres, right? So that's what I need to do now. So I have to, that's what they call outer product mean, okay? So the outer product mean would be, it's actually, conceptually it's simple, right? What I want to do is I want to basically look at ij, right? Which is along the length axis, right? So pick a slice I, pick a slice j, right? Somehow combine them, right? Which is the product, right? And then take a mean over the S, you see? So what am I doing? I'm basically producting I and j, okay? Then taking the mean over the n clust. Then I'll get ij by, whatever the dimension, and then project it to CZ, space, right? So I want to transform this from Cm to ij CZ space. So that then I can simply add another, so that's what outer product mean will do, okay? So outer product mean is a module, if you want to call it, right? So it is the fourth module, so the transition actually is the third module. The fourth module is the outer product mean. Okay, so the input to this is still in the MSA space. Okay, this is the M matrix, Cm. And what we need to do is we need to convert this into some matrix which would be Cz nres by nres. Okay, and this is n clust nres. Okay, so that's, and of course this is 256 and this is 128. Okay, so how do I go from that to that? Okay, so let's see. So what I need to do is, as I was saying, so you take your, so this is the output. Okay, if I did not make any mistake, that should be the right thing. Okay, so how do I get from here to here? All right, so let's remove that arrow. Okay, so I take this. So now let's talk about, what's happening, right? So as I was saying, here's what you're actually doing. So conceptually, it's actually simple. You pick an I, pick a j, meaning pick two slices, right? So here's your I slice. Okay, pick a j slice. Okay, so that's your I and j. Now I create, so So this is one sec. So okay, so A and B given S. Ah, yeah. So again, you can do this in you can do this in tensor form, but here they're given S. Okay. So I pick the I and j for a given S. Okay. So I'm going to describe it to you like in an element-wise manner what goes on. Okay. So in an element-wise manner, essentially, I am going to um, look at now this and this, right? Okay. So what I'm going to do is I'm going to create MSI, right? So this is, by the way, so here's what it is. Create ASI, which is a linear for MSI. Okay. And this will basically map from CM to they do this in a separate let me check, is it a separate dimension or is it CZ? No, it's actually in a different dimension, C. So what they do is they actually make C equal to 32. So in other words, this outer product, right, is not happening in 120 dimensional space, it's happening in 32 dimensional space. So I'm just first of all projecting each of these vectors, right? So that's MSI and that's MSJ, right? So the blue vector is MSJ, the red vector is MSI, right? It's the same MSI we've been talking about. So you first create a linear projection, okay? Then you create another vector BSI, which is also linear, MSI, right? And now I create the outer product, okay? OIJS, okay? So the outer product is ASI BSJ, okay? So this is the outer product. So what you basically, for a given S, right? The two vectors are basically being you're taking the product of those. Outer product means the uh, outer product meaning what are you going to get out of this? Outer product is going to get me a C by C matrix out. Okay, it's going to be a C by C matrix, and then meaning the whole thing is C by C. Okay, C by C, and then they say, oh yeah, and then the OIJ, the final OIJ is actually going to be the mean over S of the OIJS. Okay, and then finally you do the ZIJ. Well, I shouldn't say ZIJ, but the update, if you will. The ZIJ, outer product mean. Outer product mean. So, one sec, I just want to make sure I got the outer product, I get the mean, and then I need to. Oh, interesting. Okay. So this is ZIJ. Okay, I see. So ZIJ is actually just linear of OIJ. Okay, so here's what's happening. So this one is, so the C cross C, so this will be a C cross C matrix, okay, which you then flatten into C times C, and then do a linear projection on that. Okay, so let's recap, right? So essentially, I pick, right, a vector MSI, right, and I create a vector and a B vector for that, right? So two projections essentially, right? So project your 256 dimensional into 32 dimensional space. Instead of calling it query and key, I'm calling it A and B, right? So instead of K and Q, but it's the same projection, right? You're just projecting it onto a 32-dimensional space. Now what you do is, right? So this is, remember, for a given sequence, right? And this is happening over all ij, okay? So for a given sequence means S is now fixed, okay? So that's why S is a superscript here, okay? So think of S being a fixed thing for now. So what I do is I create the outer product of these vectors, okay? So these two vectors then actually, because each of them is C-dimensional vector, okay? This gives me a C by C matrix, okay? So when you take outer product, this is the actual, outer product of two vectors, right? So if you have a C by one matrix, C by one vector, okay, and this is a C by one vector, you do the outer product, you get a C by C matrix, right? So it's actually technically the vector outer product, okay? So don't get confused by this. This is your standard vector outer product. So inner product, right, is the dot product. It gives you a scalar. The outer product gives you a square matrix, okay? So if you have a C-dimensional vector, inner product is scalar, the outer product is C by C. That's all. Okay, that's what this is. So that's why you get a C by C matrix. So in other words, every ij pair, okay, is giving you a matrix out, okay, a C by C matrix. Okay. So now what you do is you sum across all the sequences, right? So the idea was to sum up all the information across all the S. So take all these like per position, right? Oj per position, you're summing up across all. So basically these are just a bunch of matrices that you just add them together. That's all, and then divide by the number of clusters, right? That's the mean. So I get the mean matrix. Okay, but this mean matrix, then you just flatten it out into a vector. So it becomes a C times C vector. And now you just do a linear projection on that, and I get my new pair representation. Okay, so the idea is that you had your original pair representation, right? We already did the row and the column attention on that, right? We already used that to create the MSA representation or update the MSA representation, right? So now I'm creating a brand new pair representation, okay? This is my new Z matrix actually. So that was the part I should have said, that what goes forward is not the old Z matrix. It's a new pairwise matrix that is coming from the axial attention, okay? Using the information from the axial attention. So that's the whole process. So now I take this, and then of course I guess they do add it to the old one, but this is the key part. Actually, yeah, they do add it to the old one, but this is kind of like an update, if you will, okay? So this is a new pairwise. So you get a new Z matrix output, or new Z tensor. And by the way, this linear is still back to the CZ space, right? So you basically go from C times C, which would be 32 times 32, to 128, okay? So C is, of course, 32, and CZ remains 128. Okay, so what you get is a new Z tensor. So that's going to give you the new, n class by n class, n res by n res by CZ. So let's call this Z new, okay? Okay, so now before we do any of the triangular updates and so on, we are simply going to add the old one back. So the old plus the Z new is going to be your updated Z. Okay, so that will be the output of the outer product module. Or after the outer product module, you basically take that and your old Z and you combine them. So information coming from the MSA part. Okay, and then now you have that. Now we'll do the rest of the stuff to this. So this I have to do in the next class. So you take this new Z, and now we have to do the triangular and multiplicative attention. But the good news here is that these attention now, when you describe them, the intuition behind them is interesting, but they are actually attention at the end of the day. Okay, so it's the same thing. Like you'll have to take this matrix and do, okay, the key, query, and value pairs. Okay, and then it's just a question of adding kind of a directionality, as we'll explain, in the next class. But it's actually, you can still go ahead and implement, because just look at the supplementary material, right? We can discuss what is the intuition behind it, but it's all the modules are pretty much very similar looking, from that point of view. It'll be key, query, and value matrices that you'll create. You'll create the A matrix, you'll multiply the A with the V matrix, you'll add a few gates, maybe a few biases, and then you get an update to Z. So now, before we're getting an update to M, we'll basically get updates to Z. So you'll have basically four things in a row. So 2 triangular and 2 multiplicative based on the direction of the edges. Okay. So we will discuss that more, but as I said, you need to start implementing this because otherwise it will be too late. All right. So see you guys on Thursday.